We are looking at special applications of diodes. This is an example of a circuit which is called voltage doubler. If you look at it, it's composed of two sections in cascade. One is a clamped capacitor, which is formed by C1 and D1, what we also called as DC restorer, this part. And then it is connected to a peak rectifier, which is formed by D2 and C2, this part. Now, when excited by a sinusoidal input VP, the clamping section provides a voltage from VD1, which is shown here, VD1. Now, if you, this is with ideal diodes. Now, you note that while the positive peaks are clamped to 0 volt, the negative peak reaches negative 2 VP. It's reaching the twice the peak voltage of the input. Now, in response to this waveform, the peak detector section provides across capacitor C to a DC voltage which is equal to the negative peak of this guy VD1, and that's minus 2 VP. Now, because the output voltage is double the input peak, the circuit is known as voltage doubler. Now, this can be used in many different cases to provide output DC voltages that are higher multiples of the input peak voltage, VP. Another application is what we call Schottky diodes or Schottky barrier diode. This is formed by bringing metal into contact with a lightly doped N-type semiconductor material. So this is what is shown on one side. Sorry, so this is silicon and this is metal which is connected on top of silicon. So there are other information, aluminum, silicon dioxide. In real, we would have much more detail into how it is formed, but generally a Schottky diode or a Schottky barrier diode is created by direct metal contact with a lightly doped or moderately doped semiconductor material, N-type especially, because we are talking about materials which will be conducting electrons. So this resulting metal semiconductor junction it behaves like a diode. It conducts current in one direction only, which is the from the metal anode to the semiconductor cathode, and it behaves like an open circuit in the other direction. So this is then the way how it would behave, and this is the symbol what we use for Schottky diode. The current voltage characteristic of Schottky diode is very much like a regular PN diode with very small variations here, or you can see the conductivity is, the values may be different, but the behavior is very much the same like a regular diode. We have to note another thing here, that the forward voltage drop is lower than PN junction, and hence we see that it starts conducting earlier than a regular PN junction, and the breakdown can occur earlier than it would occur for a PN junction. Another thing we have to note that not all metals would make this kind of junction with semiconductor material. In fact, we put metals on semiconductor surfaces to make terminals for the devices, and those terminals are, we call them ohmic contacts, because they would not have this kind of behavior when they are made. So it depends on which metal is being used to create this. So in that cases, when we make the output kind of interface with the device, those junctions are then called ohmic contacts. So just to distinguish them from these rectifying contacts of that would result in the formation of a Schottky barrier diode. Another application of diodes is what we call Varactors. So it's a reverse bias PN junction. The thing is that if you think of a diode, there's P-type or N-type material, and this is covered more in a solid state devices course. But here we can see that when it is reverse bias, there is a kind of a junction forms in the middle of those two types, which is which has less charge carriers. So on the right side, if you think about it, if there are many more electrons on N type and many more holes on P side, in this region they all are very few because of they're repelling each other. So in this part, what we have is we call it junction capacitance. So there is an additional capacitance that comes up, and this exhibits a charge storage effect, and this can be used to our advantage, where we say that Cj is, and we know Cj is a function of the reverse bias voltage Vr, which is shown here. So this capacitance is useful in number of applications. For example, in the automatic tuning of radio receivers, so these diodes, these varactors are fabricated to be used as voltage variable capacitors. So when the voltage changes across them, the capacitance would change, and hence the overall behavior of the diode would change. So we call them variable capacitors or varactors. So we are using diodes in reverse bias, and the voltage was going to change the capacitance across that diode, the charge carrying capacity. So we make these devices to make the capacitance a strong function of the voltage by changing their physical parameters. So there's more to that, but and this is how these are made. These are actual pictures shown of those. Another very interesting and very important application is what we call photodiodes. So photodiodes, these are, if you think about a diode in reverse bias, there's no conductivity, right? Now, if a reverse bias PN junction is illuminated, we throw light, and these are specific wavelengths we'll talk, but let's generalize this. We illuminate it with photons. The photons that impact the junction, they cause covalent bonds to break, which means they would break electrons and hole pairs in the semiconductor materials. And that would result into many more electrons and holes becoming available in the depletion layer. Again, the depletion layer that we were talking, the center thing between a PN junction, which is devoid of charge carriers, we call it PN junction. So this line doesn't have to be bigger than the size itself. So conceptually, I'm just putting a line just to show P side and N side. Now, this electric field in the depletion region sweeps these electrons to the N side and holes to the P side, which results into a reverse current across the junction. So, which means that reverse biased diode, it's supposed to be open circuit, no conductivity, but as soon as we turn on light, there is a photocurrent that gets generated. So that photocurrent is something that would start flowing. I'm not calling it photocurrent yet, so just the basic idea. And this photocurrent is proportional to this IP is proportional to the photons, the intensity of incident light. So let me just write lambda for photons. They have wavelength, but we'll look at this in a little bit more detail. So such a diode is called a photodiode because it converts light signal into electrical signals. We use a parameter called responsivity to distinguish or to characterize a photodiode. And this is a photocurrent equals the responsivity times the power. So responsivity R of a photodiode is the reverse current produced per watt of incident light power P. So now, higher responsivity is provided by photodiodes that are sensitive to longer wavelengths of light, because then each photon carries less energy. Hence, there are more photons per watt of light and more charge carriers that are caused because of them. Now, this is the symbol of photodiode, and there are few things we need to see here. when there's no light, there is still some conductivity, some leakage current that happens, and we call that as dark current. So D is the dark current, and minus is because it's happening in the reverse bias. And in the absence of light, this is just like a normal diode. But as soon as we turn on the light, the there is photocurrent and ID. If there was an ID flowing, now we have photocurrent flowing on top of that. So that's ID and IP. So the IV curve, the current voltage curve shifts towards more reverse current in proportion to the intensity of the light that's being absorbed by the photodiode. Now this picture is showing how we can model it. So there is dark current, and then there is the photocurrent that results because of the incident photons. So dark current places a low limit on the level of light that may be readily detected. So like all diodes, so there is again a junction capacitance for this guy as well, which depends on the physical parameters like surface area of the photodiode or the bias or the voltage in reverse bias that's being applied. Now there are more types of it. We'll just talk about another type. There is this thing what we call avalanche photodiode. So avalanche, we talked about reverse bias, and there was avalanche reverse phenomena. So here also we call avalanche photodiodes, which are biased around the reverse breakdown voltage just right there, but not in the avalanche. So what happens is a single incident photon can set off an avalanche effect, which results in more than one electron hole pair. So these are then very sensitive photodiodes, and they can exhibit much more higher responsivities. But of course, they would have to be biased at very large voltage. Now, if you look at it, if you think about it, these photodiodes, if they are used in forward bias, then they would act like solar cells. They would just be doing the conversion of light into electrical energy. So, if you think about it, they would be just doing that. Another interesting application of diode is what we use every day now is they're called light emitting diodes. So they are opposite of photodiodes. What they do is they convert a forward current into light. This is something which we use in displays, in computer monitors, in lighting, almost everywhere now where we are using light, we have replaced the old things with LEDs. So and they can produce lights in many colors. So they can design to produce even coherent light, one wavelengths as well, and with very high spectral purity, and that would what we call laser diodes. So laser diodes are used in optical communications and optical data storage and so many other things. Now, light emitted by an LED is proportional to the number of electrons and holes that would come together and what we call recombine or join together. So that energy difference would be what would be emitted as a photon and what we see as light. And we use series resistors with them because with that we can control the IV relationship to deviate from the exponential behavior. So then we can control their intensity. We can change the current in the forward bias. So when we connect them to voltage source, we can have many of them and control and don't burn them. So this is a little bit on diodes, and we will start next week with metal oxide semiconductor field effect transistors, which are devices. If you think about it, these are two diodes back to back. So this is P type, this is N type. So that's one junction and that's one junction. So two diodes kind of, if you think about it, considered back to back. So transistors are devices where we create a channel between two areas with charge carriers using a third electrode. So these are three terminal devices: source, drain, and then gate. Gate is what we use to control the conductivity between these two guys inside the transistor. So we'll get more into that next week.